name's Katherine Brown. I was John's postdoc between 2011 and 2013, and thank you very much for the organisers for inviting me to speak. So I will have to go over to the computer and move on to the next one. There we go. When Mark asked me to come and speak today, he asked me to talk broadly about 3 topics. The first one was my memories of John. The second one, which I think is probably the most challenging for me, is the physics that I did with John. And the reason I say that's challenging is I've now been out of the field for 9 years, so it's been quite a long time since I've looked at any physics. And the third one I'm going to talk about is my new career now as a patent attorney, and I will talk briefly as well about how quantum computing and patents overlap and how my career in quantum computing has moved and become relevant to my career now as a patent attorney. So I'm going to start off with my memories of John. And I think I've got a photo here that I found on Facebook of John and I, and there's Kaushik, who's here on the far, is on the right, and then there's Robbie in the middle. And that was at our Christmas party where we got some British Christmas crackers. So I think maybe the hats are less familiar to the American audience. You don't have those hats regularly, is that right? Yeah. But probably more familiar to the UK audience of coming out of a Christmas cracker and wearing the hat. So this was our Christmas party where we did a Secret Santa. But one thing I think John really tried to emphasise is he brought over students from lots of different countries in the world, and often I think in America it's quite acceptable to kind of get up, sell yourself and talk about how great you are. It's a lot more acceptable maybe than certainly in the UK and many of the other countries that the students came from. And one thing I think that John really tried to get into his students, and I think Alicia's mentioned it a bit through things like the Krispy Kreme seminar, is to get up and sell yourself and how to function in American society and sell yourself in an American society in a more American way, because that's what you would need to survive if you wanted to have a career in academia in America. So I think John was really aware of that and really tried to distill into his students this self-sense, and postdocs this sense of confidence and getting up and giving a talk to a bunch of physics professors about physics when you haven't done any physics for 9 years. But so one thing I think was it's okay to be confident, but John was not that. There was some bluster, but John often could see through bluster, and I think he liked to say himself that he had the best bullshit detector in the business. And certainly one thing I do remember was quite a vigorous discussion once in social events with drinks with Hugo, was him and Hugo getting into quite a long, vigorous argument about the relative advantages of quantum discord. I think actually Hugo came out on top of that one with it being quite a good thing. But certainly John could be sceptical, even if he did teach you to have kind of the confidence to go up there. And a lot of people have given, kind of told today and yesterday John's stories and the kind of interesting jokes that he used to tell. And I think one thing I found that's not been mentioned yet is that John used to like to say that he had a Downing exaggeration factor of pi, and that this was accumulative. So each time that he told the story, it got more exaggeration by pi each time. And I think, having heard the stories told back to me, I think everyone's heard a fairly similar version. So even if there was an original exaggeration by pi, I'm not sure. I'm sure it's a Downing exaggeration factor of pi, but it's always increasing. One story I remember that he hasn't told, and unfortunately I can't remember the names of the people involved, was him being woken up one night by campus security asking if the 3 people knocking on Mike, who's the campus tiger's cage, yelling, "Here, kitty, kitty, kitty," were really eminent professors that were visiting him. So it was good fun working for John. And one thing, and again Alicia covered this in her talk, was John was very into making sure that students were involved in going to the funding agency meetings and calls for proposals. And I certainly get the impression from one thing he said that this was something he did to make sure that his students and postdocs were ready for life in academia. And again, I can't remember the people involved, but he did tell me a story where a colleague asked him, shouldn't the students and postdocs be protected from this type of thing? And he responded saying, no, because if they do want to go on to a career in academia, then it's very important for them to be able to deal with funding agency meetings, writing proposals, and understanding how the money in academia comes in and how that influences your career. And I think these were really important lessons, and I think you can really see from John's success rate in getting his PhDs and postdocs into careers in academia, in how much that benefited the students and postdocs that he had in understanding what academic life really involved. I think despite this, and despite the fact that one of John's sayings was, the best postdoc is one who's in a long-distance relationship, because then they're neither dating nor spending time with their partner, so they can do more work. John did have actually, and let us have, quite a good work-life balance. And another memory I have of John was at an IARPA meeting where Austin Fowler, who's an Australian physics professor, had mentioned that he always replied to emails, I believe maybe it was in 24 or 48 hours, and that he thought doing less than that was rude. John quite vehemently saying that he thought this was wrong and that people shouldn't be tied to their emails all the time and did need to be off the emails, having a life, and obviously doing physics. So I think John did kind of emphasise the mixture of work-life balance and also making sure his students had the survival skills if they did want to go on into a career in academia. But life in John's group wasn't always just about work, and I think Ryan touched on this in his talk, that there were always the pizza parties, which were in my day were in the Mellow Mushroom and Reginelli's, neither of which I think still exist. Is that correct?
That's right.
Yeah, so that feels quite sad. And then the dinners where we had more eminent professors meeting, which were often in Dubon's, which John liked to say was the second best restaurant in the city, but had the best wine list. And John was also very good and obviously made sure that the conferences and networking events we went to were always quite lively. So the reason I came to John's group, and in tying into my memories of physics, was for a large project with IARPA, which John made sure I knew stood for Intelligence Advanced Research Project Activity, unlike DARPA, which stands for Defence Advanced Research Project Agency, so make sure you know what those last two A's stand for. We were doing a big project called the QCS project, which I imagine some people here or people who are in the field about 2011, 2012 know of, because it was involved physicists from all around the world. That were looking at resource estimation for quantum computing, and kind of built on the early days. It was really the original work into things like quantum compilers and quantum programming languages. And they were working in a big team with some people from what had once been called Telcordia, and I believe was now called Research Communication Sciences or something, and has now been renamed yet again. And the idea of this project was they gave you some example physical architectures, which were for official use only documents that you can't tell, but had some kind of error mechanism that they thought might represent how these architectures worked, and then to apply quantum error correction codes and quantum algorithms, oddly excluding Shor's algorithm, so it was mainly concentrating on things like triangle finding and least shortest vector and many other algorithms, and work out how many qubits it's going to take, physical qubits you're going to need to have a realistic fault-tolerant quantum computer implementing these algorithms. And I think the main conclusion we came to was that was a bit of a headache for the community. It was certainly possibly several orders of magnitude than anyone was expecting, probably more than millions. So talking about millions of qubits, not thousands. So it was quite a shock, I think, the results of that. But while we did work specifically at LSU, we were looking at some, so this is having looked at some of the papers I produced with John, so I'm going to go through them very quickly because it's been 9 years since I've looked at them. But one thing we looked at is that sometimes photonic detectors just don't click, so you just don't get a result. And we looked at using C0 gates to overcome this problem. So it's one limited problem, not that the detector's giving you the wrong result, just it gives you no result whatsoever. And we looked at different ways of arranging C0 gates to basically copy the classical information in the state and then allow you to measure it multiple times. You're still only getting one measurement result. You're not kind of doing any clever quantum metrology there. You're just trying to get one result out of this thing, but you're trying to make sure you get it clipped. And we had a look at kind of whether a majority vote or a kind of scheme where you just took the first detector works best. And unsurprisingly, the scheme where you just took the first detector to actually give you a click works best, because each of these gates is subject to errors itself. So majority vote is just building up on the errors. In the models we were given, the assumption was that if a photon is lost, then the detector gives a false reading of 0. And so we also looked at schemes that could correct for false readings of 0. Again, we looked at kind of doing majority votes. We used next gate, obviously, so that the false reading value changed between the gates. And what we found again is that majority, taking the first detector that clicks is always better than doing a majority vote. Again, that's unsurprising because each of these gates has an error on it. The other work I did with John, and that was with one of his PhD students, Oscar, who I believe is now still in the field, but I think you can ask Kaushik in more detail to know where he is, was looking at using dynamic decoupling to correct for dephasing in a polarizing containing fibre. And we used a particular type of dynamic. So dynamic decoupling is the idea, if you imagine that you've got some kind of noise that's causing your state to evolve around the block sphere constantly, then if you flip your qubit, you can allow the noise to almost take it in the opposite direction to correct for that kind of constant noise. CPMG dynamic decoupling is one where the particular pulses are arranged kind of asymmetrically, so you have L of your fibre, then 2L of your fibre, and then another length of your fibre, rather than arranging them equally distant apart. We just looked at kind of putting in numbers of wave plates with different errors on the fibre, so there are the errors on the fibre there, and looked at how many wave plates you need to kind of increase the fidelity. And I think the conclusion was you need in the region of 800 odd wave plates per unit of the fibre, and since it's been a long time since I've done this, I'm afraid I can't tell you what the unit of the fibre is. After finishing my postdoc with John, I decided to actually leave academia altogether and go on to become a patent attorney. Now, John always kind of, I think, felt like he failed when one of his students or postdocs left academia, but I don't think that's necessarily fair. John himself was always keen on saying to do what you love and to make sure you enjoy what you do, and that's a priority. And I have to be honest, I don't think academia was something that I really enjoyed, and having moved to be a patent attorney, I think that's something I enjoy a lot more. I don't think I enjoyed coming up with my own research, but I did enjoy reading about other people's research and learning about the technology, and being a patent attorney allowed me to do that. So I think to say John inspired me to be a patent attorney sounds a bit, might be not something people feel was a compliment, but certainly I think he gave you the confidence that just because you pursued a career for a while doesn't mean it's what you have to do forever, and that you should think about what you love and to do something that makes you happy, and I think he gave me the confidence to move. I think as well, John was very good at helping me with getting the job. In many ways, going back to the Krispy Kreme seminar, what Alicia was saying is he did train you to be in the seminar, to work out when you should interrupt him, and he's been going on a tangent for too long, how to keep kind of on track when people are asking strange questions or going on detours. And the interviews that I had were very much like that. They could bring in a piece of technology you've never seen and ask you about how it works. They went round in one of my interviews and just asked anyone in the office if they wanted to come along and sit in the interview just for fun. And I think having been here and with John, those kind of distractions that might have been, before I did my postdoc, quite difficult for me to actually cope with the interview, I managed to cope with quite well, thanks to John's influence and the help he gave us through training in the Krispy Kreme seminar and other things to be able to stand up and be confident. So I'm not going to go into much detail about the training process for a patent attorney, and there's a good reason for that, and that's because this is America, and in America, to become a patent attorney, you have to go to law school. And in nearly any other country in the world, you don't have to. So my experiences of training as a patent attorney are probably not going to be that relevant to this audience, even if you are thinking of becoming a patent attorney, and I think Johnny Olson, who's trained to become a patent attorney as Zapata, could probably give you better feedback on what this process involves in the US. If you're not American and thinking of becoming a patent attorney, then I've got an article out in Physics World that you can read about the process. But in terms of becoming a patent attorney, so patents, I assume, or because they're quite common in this field, they're a form of intellectual property that cover an invention. They're very territorial, so you have to apply in each individual country. I trained in the UK, and I'm a UK patent attorney, which means I can try and get patents granted before the UK Intellectual Property Office, and a European patent attorney, which means I try and get patents granted before the European Patent Office. The European Patent Office is wider than the EU, so it covers non-EU countries such as the UK, Norway, Iceland, and Turkey. At the moment, if you get a patent granted before the European Patent Office, then what you get is a series of individual patents for each country covered by the European Patent Convention. When I say at the moment, there's currently plans to introduce a unitary patent, which is broadly EU-wide, but includes some prominent countries such as Spain, because Spain didn't want to be part of it, but would include big countries like Germany, Italy, France, and the Netherlands. That's going to come in the next year or so, although that's been 10 years where it's been coming in the next year or so, but now I think it's finally actually coming in the next year or so. But that's just how it works. So my experience is very much from the UK European perspective, not the US perspective, where things are a bit different. But the requirements for getting a patent are broadly that something's novel, inventive, and industrially applicable. Industrially applicable is mainly not something we see much of. It covers most things. It would cover most quantum technologies. The only interesting thing to note is that many patent offices consider perpetual motion machines to not be industrially applicable, so that they don't have to argue with you about why it doesn't work. But novelty is broadly when something's new. Inventive step basically broadly means it's clever. I think from the quantum field, because the field is, I'd say, relatively small, although it's getting larger, people tend to actually know when their work is new. That can be a bit more surprising if you imagine in other fields, say you're doing something on aeroplane wings. There's been so much on aeroplane wings in the last however many years that people may not know, but generally you can know it's new. The clever requirement might not be as stringent as you think, because you're obviously, or you're coming from the field of someone who is an inventor, so your interpretation of what's clever might be a lot higher than perhaps kind of a member of the general public, or although we put it through the eyes of a skilled person. So the other requirement that's hidden in patents, and I think you've seen a few problems with it for people who work in the field, is that things have to be technical. So they have to have a technical effect. The European Patent Office provide a list of things that are generally not considered technical, so they have things such as algorithms, mathematical methods, scientific discoveries, and rules of playing the game, presentation of information. But then they are only, it relates to, say, an algorithm as such, which means that we spend a lot of our days talking about what as such means. But broadly, all the interpretations are fairly narrow. And I'll have a discussion about some of them a bit later for you. In terms of if you're looking for patents in quantum, things that I found quite interesting from the quantum patents is that when you're writing a patent, it's actually useful to emphasize that your things are going to, if you've got something that's happening on a quantum computer, that is happening on a quantum computer. This is because examiners sometimes interpret terms quite broadly to include a classical simulation of a quantum computer, even when that's not what you intended. So they'd say your claim had a qubit register, they'd say, well, the qubit register could just be a classical simulation of a qubit register. So actually, if you're looking at getting patents and drafting patents, and it is to a quantum computer, emphasizing things that are going on a quantum computer has been quite important. And the other thing is because quantum computing is still quite a new field, the patent office's office trying to treat quantum patents in the analogy to classical patents. So it's quite useful to use language when you're doing it that maps onto things that are more familiar for your classical computing. So compiling is often considered a technical aim, so best compile is considered a technical aim before the European Patent Office. And so if you have your quantum compiler that you're generating, then it can be quite useful to talk about a quantum compiler and doing quantum compilation rather than gate synthesis. Even though you might think that these two terms are directly equivalent, they can be interpreted differently. And I think that's quite unusual for the European Patent Office, which normally don't put so much emphasis on exact language use. So I would expect maybe see that changing in the next few years, possibly with case law. But obviously, if you're a quantum computing company, you don't want to be the one spending a lot of money to make the case law to make your point. So I think, as I said, things have to be technical, and there's an exclusion for algorithms and mathematical methods, but only in the as they relate to an algorithm or mathematical method as such. And so I think one thing that would be interesting, I don't know how many people going into the quantum computing business, is what that as such means. And generally before the EPO, you can argue something is technical for the algorithm if it has a technical effect or purpose, or it has a technical implementation. So the technical effect or purpose is probably one of the easier ones to get your head around. So broadly say, if you had a classical algorithm for controlling your quantum computer, because it has an effect outside the computer, because it's controlling the quantum computer, it's controlling another device, that will generally be considered a technical purpose. Similarly, an error correction algorithm is generally improving your computer and leading to an improved computer on the level of the computer, so that can be considered a technical purpose as well. You can then have kind of general algorithms. So if we take Shor's algorithm for factoring, which obviously is not new because it's very well known, but Shor's algorithm for factoring is just a mathematical method. It's not particularly interesting, so that wouldn't be considered to have a technical purpose. But if you use Shor's algorithm to break RSA encryption, I think that's more likely to be considered a technical purpose. I haven't actually seen any patents towards breaking encryption, partly because I think anyone doing it doesn't want to admit they're doing it and file a patent for it. But certainly when you're getting to kind of that level, if you're a company, got a quantum startup company that's developing the algorithms, then it's worth thinking about what your ultimate use of the algorithm would be and making sure you put that in the patent, and also make sure there's sufficient support that someone could implement that use. And rather than just putting in, say, your mathematical method of finding a shortest vector, why are you finding a shortest vector, what are you going to use it for, to build up to getting your technical purpose there. But I think technical purpose and technical effects do count for lots of algorithms. I mean, if you are a quantum company or you're developing classical algorithms and you want to know more, I would suggest talking to patent attorney because it can be quite a complicated field, but that's probably the easiest one, or the most common one, for arguing your algorithm isn't an algorithm as such. The other one, which I find very interesting from a quantum perspective, is technical implementation. Now, technical implementation is when the algorithm is designed and motivated by the internal functionings of the computer. Yeah, 1 minute. So you would think maybe that all quantum algorithms are motivated by the internal functioning of the quantum computer, but generally the EPO are very reluctant to accept that, and so you're going to be looking at your small algorithms that are designed exactly around your hardware rather than anything else. I had a bit more to say on that, but I've run over time, so if anyone wants to talk, I can go through it later. But on terms of leaving you, I think I remember John saying, one of his quotes was, "Friends come and go, but bosses only accumulate." It's hard to say that with John gone, but certainly I see him and his influence in my life now, and certainly that's one of the reasons that I came back today. So thank you very much, and does anyone have any questions, preferably not about the physics?
It's not about physics, but in your current job, do you follow trends in quantum-related patents?
It depends on the client. So I do keep up with what's going on now on Twitter, kind of in the field on Twitter, and what's going on with the quantum patents. Yes, but obviously we concentrate.
Do you
on
ever use some of the search engines and do analyses?
Occasionally.
I'll talk to you.
Yeah. Yes.
Your fourth to last slide. You don't have the number, so
Yeah.
that one, yes.
Yeah.
I found the second bullet to be rather interesting. And I'm curious because you're making a distinct, there's a distinction to be made here between patents referring to quantum devices and patents referring to simulations. Yeah. There's also this kind of nether realm of quantum-inspired solution, quantum-inspired hardware, things that might appear to be quantum, but they're not really quantum. They're doing something different from just a classical simulation. And I'm kind of curious how that fits in the patent world when you have a patent that's talking specifically about a quantum device.
I suppose if your device is something that you don't know what it is, or kind of a hybrid device, making sure you describe the device in detail and that it's occurring on that device and isn't just a simulation of that device would be how I would have it as an analogy. Does that?
Yeah, it would be something that's an analogy to a quantum system, say, not a hybrid, but and so it's distinctly not quantum, yeah, but it's distinctly not a simulation.
I think if it's, so it would be kind of by analogy, you would make sure you describe the physical device that it's occurring on. So if it's not a quantum computer, it's a kind of analog classical computer, to kind of describe, it's occurring on this analog classical computer rather than is.
Right. So if you have a patent that describes this as a quantum device, is your patent still good for that?
Probably not, but then I would so I was thinking more in the case where you have something that is going on a quantum device. So if you don't think your thing's going on a quantum device, then you describe the device that it is going on. Would that make sense?
Sort of.
Sort of. I'm not sure I quite understand your question, I'm afraid.
Yeah, it's a tricky question.
We can talk about it after.
So the way you describe it, there are many ways to represent an algorithm. You say a pure algorithm is not patentable, but so you can describe an algorithm as a list of steps, or using gates, or you could go really in detail and you could draw like a physical circuit that does the same thing. And when you get to that technical drawing, that is patentable because that's literally the machine. If you think about like an electrical circuit, right? You can say I've designed an electrical circuit, that's patentable. But it seems like depending on how you represent your algorithm, there's a point where it is not and a point where it is. Where is that sort of transition?
Well, this is where I think it's quite interesting. Is in at the moment, I think the EPO are kind of reluctant to accept that even on the gate level, so describing your algorithm on a gate level would be patentable. But this is where quantum is still in a very different field to classical, because we don't define our algorithms in classical computing on a gate level. And there isn't any real case law, as I said, established on it. And I think it comes down to trying to see it very much like classical computing. I think Scott's got.
Yeah. So I've only ever done one patent. It was for a scheme for cryptographically certified numbers from a quantum supremacy experiment, right? But the key thing that this, I'm excellent patent attorney, explained to me is just you cannot call the algorithm an algorithm, right? It's just, you call it a protocol, a process that's involving a physical quantum computer, which of course involves an algorithm. So I think
I was going to say I think the US is a bit more liberal than the European patent office. I imagine your patent is a US patent. I've seen that as well when I'm doing prosecution, that I do look at the corresponding US case and they do allow things in the US that we can't get through in Europe.
I see.
So, and that's generally, you'd have to talk to Ronnie, 'cause what happened was the big Alice decision, Alice Court decision that he mentioned really changed how the US saw algorithms. So in general, even before Alice Court, lots of classical algorithms were being granted. So just going back to classical computing now, and there's been a lot more cynical straight after Alice. We found the US surprisingly difficult things that would easily get through in Europe weren't getting through in the US. And now it seems to have settled a bit. Would you agree, Johnny?
Yeah, it's a lot more permissive now, but it's still good advice not to use the word algorithm.
Yes, no, that's true. Yeah.
Because the examiners might not know the difference between what you're actually saying and what you're proposing.
But yes, the European patent office tend to look at, does it have a technical effect at the end, even if you express your algorithm, as you said, as a kind of gate level symbol. But when is it gate level? When are the gates? I think it's if the gates can be implemented on any quantum computer, then they consider it an algorithm. But when this is what I find quite a difficult issue, and I think might be case law coming out to settle it. But yeah.
So I would say this raises a really interesting question about what happens when somebody recognizes this is an algorithm that was patented, and screw it, I'm going to use this, and the patent be damned, and I'm going to not pay any license fees. How does this going to stand up in court if you play games like
Well, are they using a quantum computer to do it? Then they've stolen the protocol, you see?
Well, yeah, but does that hold up? Does that hold? I'm just wondering if that holds up.
You can, this is an area where patent solicitors and barristers get involved, so we don't do this area. There's numerous things. If you found a patent that you recognise now and didn't think was patentable, that you can do in the UK to kind of get kind of things like declarations of non-infringement or declarations of invalidity before you go ahead. It would probably be safer than just going ahead and assuming the patent's invalid.
Fair enough.
Yeah.
I'm not having any plans,
No,
but
but yes, no, certainly, generally, even in patents on really obviously technical things, such as an aeroplane wing, if there's an infringement case, there will be a counter validity case.
Yeah.
So you would expect validity to be decided. US, I think that might be slightly different because the examiners, in the UK and Europe, there's no assumption in the court that the examiner's original decision was correct. I think it's kind of a slight assumption, but it's not taken as read. But I think it might be in the US too.
I think it's generally considered to be correct, but I mean, there's usually post-grant review if you're interested in like, hey, we want to get around this patent, right? So you'd actually go and petition the patent to the patent office. They would have a review, and that would likely stand up very strongly in court. I mean, you can still complain about it, and it's possible to overturn it, but unless you have a very, very strong argument that the examiner made a mistake, then it's not like.
And also, I think realistically, people use things like that to negotiate lower license fees.
All right, if there are no more questions, we're gonna charge ourselves up, folks. Coffee break.